Yeah, don't notice this when you're a kid. All right. Now, we got that transformer. So, quite an easy lesson to have a look at here. So, we will study transformers. Not these ones, I'm afraid. You know this word. It's not as exciting. It's these transformers. Which, yes, it's very boring looking. Have you heard of transformers like this before for voltage? Yeah, it converts the voltage, doesn't it? And in fact, when you think about it, it's extremely simple. This diagram is not so clear, so I'll just draw it here. Basically, you need really just three things. What are the three things you need? So the first one you have is this. This is a piece of iron, isn't it? Iron core. Then what you need here you need an AC supply, and this has a voltage P or V1, and this is and it has there's turns here. We'll say N1. This is called the primary side. Then on this side, you just have basically just a copper wire, and there's N2 turns here. And what happens is a V2 is induced, meaning a voltage will appear on the right side. Now how and why we'll look at in a moment, but this is basically a transformer, and you can make it at home. You just really need a piece of iron. Quite remarkable. Because these guys here, these are already AC supplies. Wow, what happened to you?
I was waiting.
I heard you were an hour late yesterday.
Oh, yeah.
Don't you live 5 minutes away?
Yeah.
Yeah.
Taking that when I slept.
Yeah, okay.
So it doesn't have to be in that shape.
Doesn't have to be. Doesn't have to be. I think you should draw this, please. Yeah.
I watch Transformers so much. One time I could tell which movie it is from just what's that call from when I heard the background.
How many movies have there been now?
One,
I haven't
two,
seen the latest two.
4? Yeah, 4.
I thought those movies get worse.
Yeah, they do usually do own franchises that try and drag out. Like
Not
the
always.
worst case is Fast and the Furious.
Are they like on 7 now or
Movies-
something?
No, there's like 9 of them.
What?
And they still got like another 3 more left.
But I did see that they were planning to release the next movie as 2 parts or something.
So trash.
The premise is the
As
same
a
each
physics
time,
teacher,
isn't
you
it?
would see how much how many laws of physics are
Yeah, okay.
How do you feel about Optimus Prime?
I was watching a clip of where, like, in one of them they used a car to, like, defeat a submarine or
Oh, yeah.
I was watching on YouTube going, yeah, this is mad stuff, alright. I had an engineering student like 3 years ago, and he loved those movies. He said they were the best movies ever. Right, do you have that drawn? Yep. Now, we need, well, okay, so we'll need to give you the definition. Do you remember from electricity? Was there any device that we had in electricity that changes voltage? Do you remember any device in electricity? Yeah, I was thinking of something else though. We had a whole lesson on it actually. It was the last lesson in electricity, I think.
Oh,
Thingy.
potential
Thing.
divider.
Potential divider, yeah. What was that used for?
For like
reduce voltage.
Yeah.
The big advantage this device has over a potential divider is it can be used to both increase and decrease voltage. Yeah? Now, the definition. So a transformer is an electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. The induction produces an EMF across the conductor, which is exposed to a time-varying magnetic field. Commonly, transformers are used to increase or decrease voltages of alternating current. Now, a little bit too much here for the exam. Let me tell you what you need as a minimum. Maybe actually I'll summarize it here in my own words. Oh, I think you're in the wrong room. I think you might be the other building. A transformer is a device used to change the voltage in a supply by the use of induction. And there are two types of transformers. Type 1, step up, and then 2, step down. And you can guess that a step up transformer increases the voltage, and a step down transformer decreases the voltage. Here's a transformer right here. This
But isn't it a
Two-
DC to DC?
yeah, it's two devices.
Yeah.
It's changing the AC to the DC, and also it would have to step the voltage down from 220 to probably like 12 or something. $19.5.
19.5 voltage output.
From
Yeah.
two,
From 220 up it can handle up to 240 input. We'll step it down to 19.5. Yeah, continue. So, oops. Now, oh yeah, let's examine how it works so we can get a formula. Okay, so you know here that on the left, Faraday said voltage. Oh, right, okay.
induced.
Sorry. Yeah, the induced current here, so I'll call that V2, equals minus N1 delta phi over delta T. This is the current that's induced. Sorry, I did it the wrong way around. The current that gets induced into the second wire here from the current of the first wire. Okay. What's interesting though is you can look at it the other way around. So you could say V1, I'll put it on the other side here, V1 equals minus N2 delta phi over delta T. Yeah.
N1 and V1 equals.
Yeah, so what you can then do is say here V2 over N1 equals V1 over N2, or in other words, V1 over V2. Oh, I think I've done something wrong here. My ends are the wrong way around. V1 over V2 equals. That's wrong. I had that upside down somehow. Yeah, what did I. Hang on. Let me go back here and just double check.
V2 and 2.
Huh? Say again? This should have been something else? V2? Oh! That's not N1, that's N2.
Yeah.
Thank you. It should be the number of turns here. Yeah. And sorry, so then did I do the same thing here? Yeah, this should have been N1. Thank you. So then I can say V2 over N2 equals V1 over N1. So then you get V1 over V2 equals N1 over N2. And that is our transformer law. Tells us what the voltages are if we know the number of turns. It's just a ratio, that's all it is. It's as simple as that. I think I would like you to write this little proof down. It's not too bad. Sorry, it's proof goes here, here, then up here, then down there.
What is like the actual efficiency of transformers?
I'm about to talk about that. Did you write that proof down? It's not a mad proof.
So are we sticking with the capital N?
Yeah. Okay. Yeah. Yeah. Yeah?
Yeah.
Diego?
Yeah.
Yeah, okay. However, since energy is conserved, and if the efficiency is 100%, we can state the following. So if you think about it, you have the formula VIR. No, apologies. So if I go back to this picture, there's a power input here, isn't there? And a power output. Now if you look at this example, power comes in here, power comes out here. What happened to you? Oh, come on. Okay. So, what was I saying? Oh yeah. Power comes in here, power comes out here. If this is 100% efficient, then this should equal this. Now in real life, is it?
No.
No. Where is the energy lost? Yeah, you can actually feel the heat.
Some sawmills.
Yeah.
Coal line.
This one, yes, I can hear a static inside. This one mostly heat. Mostly heat. So if it was efficient, you can say P1 equals P2, which means I1 V1 equals I2 V2, which means V1 over V2 equals I2, I think it's the other one. But if I remember that V1 over V2 equals N1 over N2, then I can get the second formula, I2 over I1 equals N1 over N2. It's opposite way around. So you can actually say power in equals power out, therefore this formula. So I think the proof, again, you could write it down, it's not so long. can I scroll over here? So I think it's maybe worth interesting to see in real life, power 1 will be bigger than power 2, won't it? Which means I1 V1 will be bigger than I2 V2. Which means, where have I gone? V1 over V2 is bigger than I2 over I1. V1 over V2 equals N1 over N2. So N1 over N2 is bigger than I2 over I1. So it means I2 over I1 is actually smaller than N1 over N2. So it's equal here, but in real life, I or L, I think it's actually smaller. If the efficiency is not 100%, you have to have 100% here, efficiency.
Which is never the case.
No, it's not. No.
Highly improbable.
Yeah.
Like, I mean, that
There's too much heat coming out of the transformer. You know, you can actually feel the heat coming out. Right. So here's a very, very simple question that I'm sure you can do in a few seconds. A small toy needs 6 volts and it gets its power from a 220 volt supply. The primary, is that 1 or 2? Is that N1 or N2? N1 is 4,400. So tell me what N2 is. Now before you calculate it, should it be bigger or smaller than 4,400?
Small.
Small, okay, so see what you get.
In a ratio 22.
Yeah. 120. Let's just see. Sounds reasonable.
Yeah.
Gina, what you got? 120. Lynn? Did you get it? Lynn? Did you get it? Are you sure? Yeah. Diego? What's wrong, Lynn? You don't look great. What's wrong with you? Did you get it or not? You need to write it down? Yeah, okay, fine.
can't do it.
That's okay, that's okay. I just want to make sure you can get 120. This isn't quite as hard as ABC yesterday for ratios, right? Yeah.
It comes saying something.
Huh?
It comes saying something.
No, it's blanking me. Right, did you get it, Lynn?
Yeah.
Are you sure? And you get it? Yeah? Okay. Right, next example. Oh, no, I just want to have the one example because it's so easy. What we'll do this morning, got plenty of time. I'll let you try these for a few minutes and then we'll start the next lesson, which is Coulomb's Law. Nice. Okay. Yeah, we're doing great. We're doing great. Coulomb's Law Part 2. Too Fast, Too Furious. We'll do next. This is just we haven't quite done Coulomb's Law, but we kind of produce Coulomb's Law from existing formulas we have anyway. So we'll do that in about 10 minutes or so. How many questions do you have in the database there?
Oh,
Probably a bucket load.
16.
16.
16.
I don't even think I have 60 exam papers, I'm not sure. This is good for you. They love this question in the exam and it's very easy. You know, it's a good thing.
Yeah.
Guys, the only way they can, just before you start, the only way they can make this a little bit harder is if they do something like this. Efficiency equals 80%, okay? But please note, you still have your formula V1 over V2 equals N1 over N2. But I prefer to think about it like this, and then you have the formula P2 over P1 times 100 equals the efficiency. Do you remember we did this one in mechanics, I think? Yeah, so you just have this and this. I don't think this changes with efficiency, because when we think about the proof of this, we used Faraday's law, whereas when we think about the proof of the other formula with the current, we used the efficiency is 100%. Okay, so I think it's only the current that changes when you have inefficiency. Less current means less power, because power is current time voltage. Yeah? Is that okay with everyone? Yeah, okay. Right, try those for a few minutes.